Okay, these are the solved problems for Chapter 10. Take a second to read the problem. I've already drawn the table, and what we're asked to find is what is the force due to the atmospheric pressure that's pushing down on it, which we know is going to be 1.013 times 10 to the 5th pascals, where a pascal is a Newton per meter. We know that pressure is defined to be the force per unit area. So we can say that the force is going to be the atmospheric pressure multiplied by the area of the table, where the area of the table is simply going to be the length of the table multiplied by the width of the table. So the force is going to be 1.013 times 10 to the 5th pascals multiplied by the length, 1.7, multiplied by the width, 2.6, and the force is going to then come out to be 4.48 times 10 to the 5th newtons. And you ask yourself, wow, that's a huge force. Why doesn't this table go flying down or through the floor? Well, if we look at the second part, what is the force upwards? Atmospheric pressure is, of course, pressing up as well. It's going to be applied over the same area, so the force upwards is going to also be 4.48 times 10 to the 5th newtons. That's on the downside of the table going up. This is the top going down, so the forces are going to balance each other out. In problem number 17, we have a water tank feeding a house from a height. Great way to get pressure with simply using gravity and not using any pumps or anything like that. The water tower is 6 meters high and it's on top of a hill. We're not given exactly how tall this hill is, but we can use trigonometry to say that the height is going to be 75 multiplied by the sine of 61, or 65.6 meters high. The pressure at the base, which is also going to be the gauge pressure, the pressure above the atmospheric, which is what all gauges are going to read, is simply going to be the density of water multiplied by gravity multiplied by height. This is equation 10.3a. And we know that the density of water is 1 times 10 to the 3rd kilograms per meter cubed here. Gravity is always 9.8. And now the height is going to be the 6 meter tank plus the 65.6 meters from the hill. So the gauge pressure now is simply going to be 7.02 times 10 to the 5th pascals. How high would it come shooting out if the water pipe broke at the front of the house and we ignore friction and all that good stuff? Well, in that case, all of that pressure, all that gauge pressure, is simply going to go back into the height. So this pressure is simply going to be right there, and I'm left with, it's going to fly up to the very tippy top of the water tank. That's how high it's going to go in an absolutely perfect world. That height is going to be 65.6 plus 6, so that height is going to be 71.6 meters. That's how high it'll come shooting out. Number 24, we have a geologist that finds a rock, and he knows how much it weighs, he knows the mass of it, he knows it's got some weight to it. He goes ahead and he submerges it. Now it's going to have some buoyant force pushing up on it, and he's going to then be able to register the apparent weight indicated by that prime here. This is very, very, very similar to the example worked out in the book 10.8, where this is going to be my mass, and now this is going to be my apparent mass. Again, that prime simply means apparent. So we can write, following example 10.8, the apparent weight as being the difference between the weight in the buoyant force right there, I can isolate what the buoyant force is going to be by adding it to both sides and subtracting the weight, or subtracting the apparent weight. So now I've written my buoyant force as the weight minus the apparent weight. I know that the buoyant force is going to be the density of the fluid that it's been submerged into, multiplied by the volume that is displaced. In this case, it's going to be the rock, and gravity. So it's going to be water that he submerges it into, the volume of the rock, and gravity. And I know that mass and gravity are related to the weight, of course. Here I have my apparent mass, and my real mass is right here. Now the nice thing is gravity goes away. And lastly, I know that the density of an object is going to be its mass divided by the volume, so I can write the volume as the mass divided by the density. So now I have the density of water multiplied by the mass of the rock divided by the density of the rock, where I've simply rewritten volume right there. That's going to be the mass of the rock minus the apparent mass of the rock. Now solve this for density, multiply both sides by density and divide by this quantity, and I get an expression for the density of the rock being related to the density of water, the mass of the rock, and then the mass of the rock minus the apparent mass of the rock right there. I know what the density of water is. That's going to be 10 to the third kilograms per meter cubed. This fellow is so kind as to measure the mass of the rock to be 9.28 kilograms, and the mass of the rock is 9.28 kilograms. Subtract that from the apparent weight, which this fellow also measured, 6.18 kilograms, and we're left with the density of the rock simply being 2994, and that's going to be kilograms per meter cubed. Okay, so here I have a raft, and this raft is completely submerged in water, and it's made out of a whole bunch of soda bottles. And on the very tippy top of the raft, we're going to have the weight of the child pointing downwards, and pointing upwards we're going to have this buoyant force. And the child is just barely able to float, so this guy is just barely under the water right there. So what that lets us do is that lets me write my buoyant force right there be equal to the volume of one bottle multiplied by the number of bottles multiplied by the density of water and gravity, simply Archimedes' principle. That is going to be equal and opposite to the child's weight, which is going to be the child's mass multiplied by the child's gravity. There's a perfect balance here. So we know that the buoyant force must be equal to the child's weight. So volume of 1 liter canister multiplied by the density of water, that's what it's submerged into, multiplied by gravity, must be equal to the mass of the child multiplied by gravity. I'm interested in this number n here, so n is going to be the mass of the child divided by the volume of one 1 liter bottle and the density of water. Now the volume is going to be 1 liter. This is the metric system, so we need to work this in cubic meters. That's going to be 10 to the negative third cubic meters. So mass of the child, 32 kilograms, divided by 10 to the negative 3 inverse or cubic meters. And then the density of water is going to be 1,000 grams per cubic meter, so you can see why this had to be in cubic meters then. And we're left with the number of bottles being equal to 32 1-liter bottles.